So today we'll discuss various ways to solve or various ways to figure out the possible solutions of time independent Schrodinger equation in 1D. And as I as I already discussed that why it is important, because generally you have to know the solution of this time independent eigenvalue equation to know about dynamics or any other. It's anyway good to have one complete set of states, and generally conventionally it is the Hamiltonian's complete set of states, Hamiltonian's eigenstates, which you know as the complete set of states, to know various other properties. Like you can express any arbitrary states in terms of these, and you can look at dynamics or any other problem. Since most often historically and also technically, even not just historically, even current times, that the most common type of experiment that you do is basically spectroscopy, right? And spectroscopy is basically energy difference measurement. So that is why from statics point of view it is a very important problem to deal with the Hamiltonian equation, right? To solve the Hamiltonian eigenvalue equation. And dynamics anyway, that I don't need to tell you, because dynamics is Hamiltonian is the generator. So that's why this is uh, like from now to a bulk of, usually a bulk of quantum mechanics 1 course is devoted to solve this problem. Okay. So that's what we will do. And we earlier discussed 3 theorems for which I gave you an intuitive proof but not a rigorous proof, which you can find in any books. So one first is 1D, no degeneracy, and second is can be real, it's a choice, and third is if Vx is equal to B minus X, then eigenfunctions are either odd or even. So I will add two more theorems, two more such generic statement about the mathematical properties of the solution, and again I'll give an intuitive proof. So let me just list them here, and we will see that in a moment. Okay, one of them is node theorem. I'll explain it in a moment what is it. And another of these, it is kind of a corollary to this, it's not a new statement. Alternating states will be odd or even provided this Vx equal to V minus. Okay. So one more theorem we will do today. Okay. But let's see what is the general structure of this solution. I gave you a bit of hint last time, but now I will do it a little slowly, the same thing. And so let's see that what are the kind of problems we will do, and what are the different structures of this solution. So as I told you earlier that we are going to do 5 kinds of problem. The first is nice potentials, that is continuous, and a physicist's definition of continuous is you can draw it on a page without lifting your hand. Okay. I mean, if the mathematicians will freak out if I define continuous like that, because you are supposed to take limit from left side, right side, and all those things, all those rigorous check. But a working check is if you can sketch, for example, this potential, this function. This is not a continuous function, right? At x equal to 0. But anything that you can draw like this, is continuous because you can draw it without lifting your hand. Okay. So this is the crude check. Yeah. So can everyone hear me, and can you speak up once? What they are saying something? Yeah. Don't. I cannot see your screen. Okay. So speak up. Can you talk that directly? That I want to check also if the speaker etc. is working. Can somebody speak
Yes.
a little louder? Can we make it louder?
Can you hear, sir?
This is the microphone laptop speaker, right? I need it to be in the hall speaker. Can you speak? He's saying something. Huh? Okay. Okay. So what we'll do is that we'll see what are the possible properties of this solution. So first of all, so this thing, okay. So two properties we definitely demand is that both psi and psi prime are continuous. Okay, this has to be there. Okay, why not? Because I mean, why they has to be continuous? Of course, you will see one some cases where the psi prime is going to can possibly misbehave, but we'll come to that. But they are also physically consistent. But psi definitely should be continuous. There are two ways to see that. One is a very quick mathematical way, is that if psi and psi prime are not continuous, then psi double prime is not well defined, right? If there is a discrete jump in psi prime, it's not a continuous function. If psi is not continuous, psi prime cannot be continuous. If psi prime cannot be continuous, or psi prime is not well defined even, but let's say psi is well defined, but psi prime is not well defined. It's some has some discrete jump. Okay, so it can happen. For example, if you have a function like this, its derivative will behave like this, right? Will have some jump. So in that case, the psi double prime is ill-defined, and if or if psi double prime is ill-defined, then there is no Schrodinger equation, right? So this is a very simple mathematical criteria. But physically also, if you think, although for psi we don't have a psi prime, we don't have a physical argument. For psi is basically some wave function that represents the probability amplitude of finding a particle in this position space, right? This is the psi. Now, you naively physically expect that if I take a point and I approach from right hand side and left hand side, it should be same. Right? So this is a naive physical expectation. Whether a particles you will find it, that should not depend on whether you are limiting it from left to left or right side. So that's why you don't expect a function of this form, to be a legal probability, a legal probability amplitude, and this is a simple and mathematically also it is true. It cannot be so that when you are approaching this point from left side and right side, you will get wildly defined result. Okay. So, and mathematically also it is, as I argued, that it must be true, because otherwise it will not even satisfy a Schrodinger equation. And what we are trying to find is the eigenfunctions of this time independent Schrodinger equation. Okay. So these are the 2 points, 2 criteria which I argued mathematically and physically, and let's see what else can happen. Okay. So can they speak now? Can I hear? Okay. Okay. If some can you type at least, if the since the IT person is will come sometimes. If you have a question, okay, speak up. Let's see. I can hear it. Shubhadeep Datta, can you hear me? He's saying something, right?
Yes, sir.
Yeah, but are you you have a question, right? You raised a hand. Now he removed that hand, so it's not. Anyways, okay. So let's see, there are two criteria. So they both has to be continuous, and psi has to be single valued at least. Psi prime also has to be, because that's some physical. You physically you expect that, but mathematically at least it should be single valued. Single valued, for simply because of the reason that there cannot be two different probabilities or two different amplitudes of finding a particle at a particular point of in space. Like this is a naive physical expectation. Okay. So with this criteria, let's see what are the possibilities. Okay. So first is, let's say, now where things can go wrong is the Vx. So v here it is nu x, by the way. So again the notation problem might come. So V scaled with 2me by h cut square is nu. Okay. So the nu can be misbehaving, right? So let's see what are the possibilities. So the first case is nu x is continuous. Then everything is in order. Okay. Then psi prime, psi double prime, all are continuous. Let me just write continuous. So this is first case. Next case is, so this is true for most cases, right? Most potential will be well behaved. Okay? But there are very interesting potential. Nu x has finite jumps. You can have a potential which is like this. Okay? This could be. Okay? Now, this is a continuous and well-behaved function. It is multiplied by a function with a finite jump. So this is of course a function with finite jump, right? But if this has a finite jump, that means you can say this much, that psi double prime will have finite jump. But since psi is continuous, psi and psi prime, they can be continuous. Okay? They can be continuous. There is nothing that prevents that. At least psi double prime doesn't have finite jump. No finite jump, because psi didn't have finite jump. But psi prime must be such that it has a, that the when you take a derivative on that has a finite jump. Okay, which means it could be something like, what is a good example of a function with a finite jump? So if it is like that, okay. So for example, the derivative in this side and this side could be different. Okay? The sign of derivative, therefore it can have a finite jump. So this is a allowed behavior of psi prime. While this must be well smooth, but this could be something like that. And then if this is like that, its derivative in two sides will be different. Okay? So this kind of properties are sanity check. Okay, these are sanity check. I will of course rigorously solve the problems, but this is let me give you a general intuition that a general idea. So it's very important that you know a lot of properties, or as much as possible properties of a solution before you solve a problem. Okay? Before you start to solve, because there are many ways to make a mistake. And how you know you are making a mistake or not is if you have this kind of idea that what are the possibilities in a given problem, and whether your solution is violating all those possibilities. If it is, then you have to go back and see why it is violating. So these are the steps to solve a problem. If you don't do these steps, then there is no way to know whether what you are doing is right or wrong. Okay? So now a third possibility. Now nu x is now this is a very tricky problem. We will discuss this separately. So nu x is a delta function. If it is a delta function, that means this is continuous. This has a delta function. That means there is an infinity, right? So that means this also, there must be an infinity here also. So this is a case. So that means psi double prime is also delta function. Delta function multiplied by a continuous, it has at least an infinity somewhere. Okay, but means psi prime must also have jumps. Okay? You cannot have a delta function unless you are taking a derivative of a function which is jumping. Like the psi prime must be also behaving like this. This is what is required for this. So let me draw it here. It must be behaving like this. Now that is not the case. You didn't expect this, because if you take this point, left limit and right limit don't match. So this is a case where psi prime may not be continuous, but psi has to be continuous because that's a physical requirement. Now the fourth property is there is a hard wall. So nu x has a hard wall. Hard wall means what? That means the problem you did already, particle in a box kind of problem. Hard wall means there is no way the function can exist outside this. So if that is the case, then the function is continuous in this domain. But since the function must vanish here, whatever happens in the middle, anything can happen in the middle, it must vanish here. That means it is not continuous at this point. So this in the wave function is not continuous, but there is no problem for that because it's the domain of the function. The function doesn't exist beyond that. So in that sense, there is no problem. You are still following the basic criteria that psi must be continuous. Okay. So these are the four properties, general properties, which you will. These are all the kind of problems that you are going to encounter. And now let's see the general structure of these solutions. What happened to?
Sir,
Yeah, questions?
yes, sir. Sir, just by seeing that equation, how are we determining whether mu x will have
Sorry,
finite
sorry,
terms
say
or
that
not?
again. Sorry, say
So
that again. I can't hear properly.
just by seeing the equation, how are we determining whether mu x will have finite jumps or not?
What finite? Okay, just a moment. They are fixing the audio. Anyway, let me continue, and I'll of course I'm not wiping the board, and we cannot lose a lot of time like this. Okay, past and fourth. Yes. No, in the sense that hard wall means it is not defined over the entire domain. So it's only defined in some finite domain. Hard wall means this thing. So these are all the four possibilities. So why it is, so this is of course not continuous because there is an infinity here and the particle cannot go here, right? So if you approach the wave function, if you look at the wave function must vanish at this point, right? Yes, it's not, it's but there is infinity here. So how do you define this potential? It is 0 here and infinity here. So Vx itself is not continuous, right? And therefore the wave function must vanish at this point, and that is one case, one special case just of this. Okay, that way you can think. Is it okay now? Okay. Okay. Yeah. So can you ask your question again?
Hello?
Yeah. Tell me.
Yes, sir. I asked like mu x has jumps or not. How are we determining just by seeing the equation?
No, I'm just saying the conditions. That is what I have been talking about throughout this time. What I'm saying that if nu has this property, right? So nu is a problem. Is a in this problem the what you have defined from outside a priori before solving the problem. What you know is the structure of the potential, right? So given the property of nu, given this is the property of nu, you know, you can tell that what could be the possible nature of the solution of psi. Okay, do you understand that now?
Yes, sir.
Yeah, so it is the when you are solving a problem, your nu is something that is given, right? That you somehow have figured out from the problem, or if you are solving a exam problem or assignment problem, there the nu is given to you. Right? So for example, particle in a box. Okay, so mu is already defined. This is the potential. Harmonic oscillator, the problem is already defined. The problem of tunneling, right? This is the mu. This is all these things are already given to you. Now I am telling you that given all these possible behaviors of nu, these are all the possible behavior, either continuous or finite jump or delta function, or it has a hard wall. If these are the possible scenarios, then what can you tell about the solution without solving the problem? Okay, so that is the goal of this part. So
So I have a
now,
question.
yeah.
In the second case where your U of x has finite jumps,
Huh.
so how will we argue that if psi is continuous and your psi prime has no finite jumps, whereas your psi double prime has a
No,
finite
I'm
jumps?
just saying that it is possible. It is possible. So one thing I can guarantee that psi is continuous, right? That much you agree.
Yeah, yeah, that's fine.
Now, if nu has a finite jump, then psi prime must have a
Yeah,
finite jump,
yeah,
right? So psi double prime must have a finite jump. Then psi prime, they need not have a finite jump. That is the point. Okay, it's not
okay. So you are
guaranteed.
just thinking of a sub case of that.
Need not have a finite jump. Need not have finite jump. So that is what I'm it's not a, because as you know that you can have a function, that's the example I gave you. One side is positive curvature, another side is negative curvature. So if you take the derivative from both sides, they will not be a continuous, they have a finite jump, right?
Yes, sir.
Okay, so what I'm right now discussing is the realm of possibilities. I'm not discussing a specific problem with a specific solution. Okay, just such that when you actually solve a problem, you will know whether you are making sense or not. This is also one lesson I want to make sure you are very careful about when you are writing exams. So I found that different levels of mistakes. Okay, people have made a mistake in algebra, in arithmetic. It's okay, that happens in exam pressure. It happens. There is not much penalty for that. I said 50% marks I'll reduce because some people were very clinical and accurate. So if I don't give them some penalty, then it will be unfair for those who are very accurate throughout the problem. So that's why there is some marks reduction. And if you want in the end same, I can even make it less. Like if you make a small arithmetic mistake, the penalty will be less. Okay? That's, I don't mind that. But if you are coming up with an answer that probability is an imaginary number, and then all kind of crap, like writing a matrix, and then somebody came to argue me why I didn't get marks for eigenvalue because you didn't calculate any eigenvalue. So then such a person is dangerous. Okay, dangerous to trust or with anything. So make sure that you understand these kind of things very well, because let's say you are given a problem in exam or assignment anywhere, you made a mistake in the problem. Now what kind of mistake is that? Is it a small calculation mistake, or it's a mistake where you take the solution in which is impossible? Okay? Impossible to have for that kind of problem. So if the latter happens, then such a person, that means didn't learn anything. Okay, if they made a small mistake, they will find it. They will find it if they had given more time. It is not an exam, it's a, they have a more relaxed environment, they will find it. But if a person cannot distinguish between what is a possible solution and what is not a possible solution, that person should not get any credit. So that's why make sure you understand these things very carefully, that such that you at least know a possible solution. Okay, so now I will talk about a generic problem which I ask you to revise a bit from your high school calculus, is that how do you solve this differential equation for various scenarios? Okay. So we will assume this, we'll take a shorthand of, for this quantity, call it minus kappa square. You have done this kind of problem probably many times in school, and so if I sketch the potential. So let's say this is a general. Again, I am talking about this. Very important that you learn how to solve, how to think about a generic problem, because there are infinite varieties of problem that I cannot do all in the class. But I can tell you how to think about a general problem and then give some example. So let's say a generic potential, which looks something like that, and that means the solution could be of this form. So let's say this is the energy. So that means this will have this possible solution as, if the energy is somewhere here, then there are three regimes. I call it regime 1, call it regime 2, which is between this and this point, and call this regime 3. So let me write this as regime 1. Okay. So what happens in these three regimes? So let's look at regime 1 and 3. So 1 and 3. They have the common property, but in both places the potential is higher than the energy. So that means this minus kappa square, I told this quantity is minus kappa square, is a positive quantity. So if minus kappa square is positive, that means kappa is imaginary, purely imaginary. So let me write down the general solution for this problem first. So the general solution you can take for this problem as a e to the power I k x plus b to the power minus. This is the general trial solution. And you also, it is useful to write down the derivative because you want to check if it is continuous or not. So let me write it down also here. I k a e to the power I k x minus I k b e to the power minus I k x. So first, regime 1 and 3 in this trial solution, we argued that the k can be imaginary, k or kappa. Kappa can be imaginary, which means the solution must be of this form. Okay, because it will be either exponentially growing solution or exponentially decaying solution. But now we generally demand, not just generally, it's a property of bound state that psi x must go to 0 as x going to plus minus infinity. Now notice this is, even if it is not a bound state, you don't expect this, that this side, when x goes to infinity, this solution is going to infinity. This part is going to blow up, right? It's a growing function. Similarly, this part, when x goes to minus infinity, this is going to blow up. Okay. So this must satisfy the property that when x is greater than 0, then psi x can be only a to the power minus kx and kappa x, and when x is less than 0, then psi x must be v e to the power kappa x. Okay, because it has to be continuously connected also. So that's why this x, these two sides will be different. At the origin they meet to be 0. So then there is no discontinuity problem. In case you don't have this middle region, if for some problem, then this must be the property. Okay, in region 1, these are the possible solutions. Now region 2, okay, so region 2 must satisfy psi x. So let me use a defined notation instead of a and b. Let me, because I used a and b here, let me write c and d. So c e to the power I k x plus d e to the power minus I kappa x, not k. And this will remain to be, because in this case, so region 2 means nu x is less than e. That means kappa is real. Okay. So if kappa is real, this must satisfy this solution. That means it's an oscillatory solution. Now you can alternatively also write these to be, so let me call it psi in region. So this is x greater than 0 means this side. So this is region 3 and this is region 2. So this is region 1, this is region 1 and this is region 2. There is must satisfy this. Now I can rearrange this term. I can rearrange this term because e to the power I k x is sine plus I cos x and d is sine plus I also sine plus I cos x minus I cos x, and write it instead as sine kx plus d cos kx. This is perfectly legal to do that because of this theorem, because I can choose the energy eigenvalues as real if it is purely real, if it is a in 1D and yeah, in general in 1D I can do that in any bound state. Okay, so now I have a structure of solution in these three part, that in region 1, 2 and 3. So notice what is the special form of this solution. In region 1 and 2, they are either decaying, they are all decaying function, they are not growing function. All this region 1 and 2, they are decaying function. So that means it must go like this. As I argued, it cannot go like this. It cannot grow like this, because if it grows, it will go to infinity. Right? At infinity, the wave function will be infinity. That cannot happen. Such a thing you cannot integrate. You cannot normalize. So it is not a physical solution. That's why I thrown out the other part. Okay, thrown out means I just said in x greater than 0, b must be 0. If x less than 0, a must be 0. So the solution must be of this form in region 2, in region 3 and region 1. Now, what happens in region 2? We have seen that it's oscillated. So in region 2, it must be something like this. But you have to always maintain the thing that psi is continuous, always continuous. That's what we argued, right? So if psi is continuous, that means at these 2 points, these two must match. And for a general problem, we argued psi prime is also continuous. So psi prime also should match here and here. So that gives us two criteria. That is psi. So let me call this point A and this as B. So that means it gives us a criteria that psi 1 at A must be equal to psi 2 at B. Sorry, I wrote it wrong. It should be psi 1 and A must be equal to psi 2 at A. So that means 1 and 2 must match here, must match as this point. And similarly, psi 3 at B, psi 3 at B must match psi 2 at B. So this gives me two criteria. Okay. So this is, let me write it as 1, this is 2. Now the derivative must also match. So the derivative gives me the same thing, a third criteria, third and fourth. Psi 1 prime A, psi 2 prime A, and psi 1 prime A, psi 1 prime B, psi 2 prime B. Now this is neat. So we had four unknowns so far. So we started with actually four unknowns, 1, 2, 3, 4, and we still have four unknowns, but for a given condition we have thrown out 2 in other regimes, and we have 4 equations. So we have to satisfy them and solve it for it. So that's the job. Okay. So let's see, one more structure will emerge from there, which is also very important to notice. Where should I write it? Let me write it here, right next to it. So everybody is clear up to this? Online? Okay, good. So let's see something more we can say about the solution without solving. Well, now we are actually almost solving the problem, but we are still not quite fully solving because we don't know yet anything about the Bx. We just nu x. We just assume it is a well-behaved function of this structure. So it need not be of this structure, because the nu x could be something that is a finite lump and disappears outside. But I will see. Immediately from this picture I can construct all the possible solution. Again, this is very important to have a mental image of. So this is something I call to every year, that this is a stare and solve technique, which means you look at the problem, stare at the problem, and you have a solution in your mind already, like immediately just after seeing the problem. Yeah, psi 3. Right, right, very good. So this will be psi 3. Okay. So it's very important that you stay. This is something, but you can only come to this. You can only acquire this quality if you solve many problems. Without that, that will not come. When you do that, then you can stare at a problem and you know a picture of a solution or an approximate solution, which you prove by calculation. So that is actually the main difference between really great scientists and not so great scientists. Like people like Philip Anderson and all, they could see where a field is going in 10 years down the line, because they have a picture of the solution of many problems, right? And it is also generally true, even if you want to do a research problem, that as I said, that a calculation might take 1 year, but this 1 year, it's not a undirected random calculation. So you have a rough idea that what solution you want, and or what could be a solution. Now the idea could be wrong, it will be refined over the time, but it's better be correct, because then you are more likely to have something. And that comes only if you learn to do this kind of approximate solutions without actually fully solving the problem. So take these kind of things very seriously, and go through it slowly. And it's nothing difficult. It's high school mathematics. It's just a possible solutions you are getting guessing, just looking at the a differential equation. You have learned it for many years. Okay. Okay. So now. What we'll do, we'll see one more property. So let's use these boundary conditions on this, right? So we said there will be three. So let me draw this, because this part is a little messy. So I said there is a potential of this form, and I argued the solution must be like this, must be something. So let me write the solution here. So if this is my regime, because one plot it's difficult to see two, because here the y-axis is v, so one should not draw like that. So this should be the sketch, and the sketch is this. Okay, so this must be the form of solution for this problem. Without solving, I can sketch that much. Okay? And this will. What more can I say? That it has these 4 unknowns and 4 boundary conditions. So let's see what could be the possible solution. So let's use the boundary condition 1 and 2, 1 and 3. Okay. So you will get that C sine Ka plus D cos Ka is equal to A e to the power K. So it's not K actually, it's kappa. I keep forgetting, because K we use for momentum, but and it's not always easy to remember to write kappa and say kappa. So just if in case I say K, I mean kappa. Okay. So the third is a derivative. So it will be C cos kappa A. There will be a kappa in front, but kappa will come here, here, and here, and I will cancel all of them. So C cos kappa A minus D sine, cos ka derivative is sine with a minus in front. So this will be A to the power kappa A. So this will give you these two conditions, and 2 and 4 will give you C sine kappa A. No, it's B. So 1 and 3 is for A, 2 and 4 is for B. So D cos kappa B, B to the power minus kappa B, and this will give you C cos kappa B minus D sine kappa B is equal to V to the power minus kappa B. Okay. Now it's kind of easy to solve, because you can immediately see that these two things are equal. These two things are equal, which means these two must be equal. These two things are equal, which means these two must be equal. Okay. So let's for simplicity, let's call A as 0, A as 0 and B as L. Okay. Give it some coordinate, definite coordinate. So then you end up with this condition. So of course you can solve this 4 equation and 4 unknown. That will be something you know how to do. But this obviously tells you that, so D must be equal to A and C must be equal to, yeah. So let's take the condition that C equal to A and D equal to A. So that's a possible solution, and that will give you sin KL kappa L plus cos kappa L is equal to cos kappa L minus sin kappa L. Now when you put everything together, you will see that, so you can take this cos, cancel it, and take the sine this side and set that sin kappa L is equal to 0. So that will give you the condition that the kappa must be 2 pi m by L. Okay. So that tells me these solutions are suggesting this kappa is discrete. Okay. So this is your first hint of a of quantum or discrete solutions. So all possible momentums or all possible kappas at least. So let's not call kappa a momentum right now. It's wave vector. So all possible wave vectors are not allowed. Okay, only some finite numbers. Yeah. So if I set this C is equal to A and D, so that means I am taking this all the prefactors to be equal. Okay? So these two are equal, right? So one possible solution is C, D are both equal to A. Okay. So if I take that, then this must satisfy a discrete. Now it is also generally true. It is, you can show it is also generally true, but here it is easy to see. Okay. Okay. So what else? I am seeing if I can. Yeah, it's a little messy solution, so I think I will not do it right. I'm just seeing if I can show it without writing it down like a. Let's look at this and see it satisfies, but can I directly get it from there? So let's see. So if I do C first, yeah. So use this one of those methods of simultaneous equations. What are those methods? I'm forgetting those. So or put it in Mathematica. Just put it in Mathematica and find all the possible solutions. Okay. Yeah. Yeah. Sorry. Say that again. If. Huh. Hmm. Ah. Okay. 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 Yeah. Yeah. Thank you. Yeah. So yes. Very good. So if I put a equal to, so this is a equal to 0 and b is equal to L. Okay. So if I put a equal to 0 here, the d will be equal to a in this equation and c will be equal to a there. Okay? Very good. Okay, good. So then I don't need to do it in some weird way. It's obviously true because of the 0 and L. Very good. Okay. So if I plug in that, then I know this must be equal to this. So CD must be equal to A, and then it must satisfy the discrete solution. So this is your first indication that the possible or allowed solutions are quantized. Okay? So this Vx minus E, nu x minus E, this is your kappa, right? Now this is your kappa square. Now the what it says that the kappa is discrete. That means kappa square is also discrete. Okay? And this is a general result that if there is a bound state, its possible solutions are always will be discrete. Okay? So this is the general property. Now let's now look at some example. Before I go to example, let me just tell you what are some other possible problems of this kind. So this was the first. So quantum mechanics is called quantum mechanics because historically, this is the first property of quantum mechanics that people have encountered. Right? People have found this atomic model or spectroscopy. They found a discrete spectrum when there should not be. Right? And that's why they called it quantum, like some lump. They wanted to explain it as some lump of energy packets it can absorb or emit. And this is the first discrete, so first time we are seeing that where is this discreteness coming from our formalism. And historically, since this was the first thing that was discovered, people named it quantum mechanics. But as you know that discreteness is not the main feature of quantum mechanics, because there can be, I will immediately show you that there can be solution which is not, which need not satisfy this. And the main feature of quantum mechanics is superposition. But superposition doesn't sound cool, so quantum mechanics sounds much more cool. Okay? So that's why the name stuck with this subject. Okay, now let's say I want you to solve a problem of this form. So this potential had the property that it is bounded. Bounded in the sense, as you go to infinity, then the potential also goes to infinity, right? So this keeps growing. That's what I suggested, right? Now this need not be the case. You can have all kind of stuff. So let's consider a potential of this form, okay? Which means this is your Vx. It grows here or doesn't grow. It goes to flat. Okay, it can also happen. And I have a E. So what are the possible solutions? Can you suggest the solution without solving? Can you sketch a solution? Anybody in online? So this part, E is greater than nu, right? This is the nu x. E is greater than nu. So it must be a decaying solution. And this part, so this part nu is greater than E. So it must be a decaying solution. That's what we argued. In this part, E is greater than nu. So it must be a oscillatory solution. And they must match at this point. Okay. So this is an approximate sketch of the solution without solving anything. Okay. Now this can go to infinity like that. Keep going to it because it's effectively a free particle. Energy is more than potential. Well, not exactly free because there is a functional form of this. Now let's ask another question. What if instead of this I flip it, which means I make it like this, and here is your energy. So what will be the solutions now? Just use analogy from this problem. Huh? Yeah. Anything? Okay. So this part is E is greater. So this must be like that. This part E is greater. It must be like that. Here it must decay. And they must meet somewhere continuously. So this must be the solution. Right? It's very important that you are able to write or think of a picture of a solution without solving the problem, as I told you. And this doesn't come from reading books. This comes from solving problems and thinking about them. Okay. So these are two classes. You can imagine any class, right? Think about this. Let's say you have a potential landscape like that. Okay. A hill, some crater, and some hill and crater. Okay. And this is your energy. Or this is your energy, wherever you want to put it. So sketch the solution without solving. Okay. Cook up as complicated problem as you wish, and try to think about the solution without solving. And we will not do, of course, this kind of messy problem, but there is a technique called WKB approximation, which we'll learn in quantum mechanics too, because in real world, potentials are often like this. They are not, you do not know exactly the form of potential. Let's say you have given a gate voltage in a device. So let's say you have a chip, a 2D chip, which looks something like this. Okay. And you have applied a electrical gate voltage which goes through these, and somehow it it's a metallic part, and this part it has some screening effect, then you get a rough shape potential, and you need some sketchy solution, okay, at least to proceed. Now, the kind of problem that we'll do in the course is not bad. Of course, they are well behaved problem. So what we'll do is this kind of problems we'll discuss.
Sir, if the potential is like square wave shape,
Sorry, tell
fine,
it
fine,
again.
fine. I was asking the same question what you draw in the picture. Like if the potential is square wave shape, then what will be the solution like that?
So if the picture is,
Square wave like potential, like
yeah, we'll discuss all of them. These are part of that is what we'll discuss. Like in the course, we don't discuss these things, right? So we'll discuss these. So this is a hill. This is a barrier. So this is a well, and then there will be these kind of problems. These are the problems that we'll discuss. But I want to first think about you to think about this. It's easy to sketch this solution also, right? So this solution, if the energy is here, it must be this, right? It must be something of this form. So of course, there we will show how it is like rigorously, but without solving also we know, right? So it's very important that you are able to do these kind of things. It's think in your head about the problem without solving it. Okay, now I will do a problem which you have done before. That is the infinite square well, and I will tell you that there are some couple of interesting and important thing to learn about it, which I said earlier, that node theorem, and then we will go on to talk about more complicated problems. Okay. This part is basically intuitive differential equation solving. It's really easy. As I told you, the course is going to get easier. So this is a manifestation of that. There is not much, like no strange things like quantum mechanics. The strange things have passed, and I hope now you are. Of course, there is no. It's not easy to get comfortable with it. But what we can do by looking at many examples and looking at many problems, you can get used to it. Okay, that's the best you can do in quantum mechanics. People are still uncomfortable about all the weird what is happening there, but people got used to it and trying to use it somewhere. Okay, now we'll do one of the problem that you have done in previous courses, is that infinite square wave. Right? So what was the problem? The problem was you have an infinite wall at 0 and a. Okay, you can think it again, a b, where the b is now I have drawn as 0 and a as a. Right? So this is your Vx, this is your x. So now, okay, now there is one theorem which I missed before, and but I'll tell you by giving you an intuitive proof of that. Okay. So the solution at the middle will be h cut square by 2m d2 psi dx2 is equal to E psi. Because in the middle, so the potential is this, it is 0 when x is greater than 0 and less than a, and it is infinity elsewhere. So if I look at the middle, so this is my form of differential equation. This is the equation I must solve. Now I can rewrite it in this form. Let me call it k because it is hard for me to remember calling it kappa every time. Okay. Right. And it is justified to probably call it k because it's nothing but 2m by h cut. Okay. Now if that is the case, then the solution is, as you can see, the potential is lower than the energy. Okay, now this is an important point. So we want to find solutions which are greater than 0, because I want to find solutions where energy is always greater than the minimum of the potential, which is 0 in this case. So I'll come back to this point. Why do I do that? A sine cos x plus b cos x cos kx is the solution, and it must satisfy the boundary condition. So b must be 0. Okay. So you cannot have the solution finite here. So since the potential is infinite, that means there cannot be a solution here. Now it has to be continuous. So it is 0 here. So here it must go to 0. Okay. So b is 0 from beginning. So I must have a function which is like this, at least like this. In middle, I don't know. I must have a solution which is of this form, which vanishes at these 2 points, because the potential is 0, the wave function is 0 here and here, and it can continuously match with that. So that leaves me with psi 0 is equal to psi a. Both are 0. So this is consistent only with b equal to 0. And that means also that kn. So if you match these two, the kn must be n pi by a. So that leaves you with the solution. So this is so the k can be only n pi by a. These are the n solutions. So I give it index a. So that means En is n square pi square. So En is, so I square it. So it is k square h cut square by 2m. So that is pi square n square h cut square by 2m square. Okay. Yeah, 2m square, and psi nx is a sine n pi x by a. I just replace the k's, the possible k's inside the sign. Okay. And it must satisfy this, because this is a probability, and if you put that in, you'll find the value of a that satisfies this. So you have to do this integral, a mod square sine square n pi x by a square. So solve this, you will get a value of a square, and that will give you root 2 by a sine n pi x by a. Okay. So these are the allowed energies that is greater than 0, and this is the wave function, eigenfunction corresponding to that. So everybody followed this solution, right? Everybody did it also before, but did you follow the way I did it? Okay. So now let's study some of the properties of this wave function. Let's sketch the wave functions. So I will like to make a statement, and I want to go back and check and think about it. It's all worked out in Griffiths. So the statement is, why am I looking for solution only that is greater than 0? Why I'm not going below 0? Okay. So there is a theorem that energy is bounded from below by V minimum. So it cannot have a solution if the energy is below V minimum. So I can give you intuitively why it cannot be, because you will get a solution that is growing or decaying in this region, and you will see that it cannot satisfy all the conditions. These are intuitive reason, but I want you to look it up and think about it. In this case, the V minimum is 0. That's why E must be greater than 0. Okay. So this is problem 2.2 in Griffiths. 2.2 in Griffiths, it's worked out there. Look it up, that why it must be so. But it is also very interesting to know that, and there is a physical consequence of that, which means if you have a bounded potential, its solutions or energy cannot be below a certain level, okay, certain number, which is given by B minimum. Because if you allow that, such a system will not be stable, because the system will always like to go below that. So there must be a lower bound somewhere, and that lower bound is this. So that is what you have to think and prove. Okay. Now I will make one more statement and end this class, and tomorrow we will take it up over from there. I will also discuss this statement, but I want you to look it up. So now let's sketch this solution. Let's look at this solution. So the solutions for n equal to 1 will look like this. This is sine pi x by a. So n equal to 2 will look like this. And n equal to 3. So this is a theorem. Can be proved generally. Okay. So this is how you know all this. You know the drill, all this solution. Now later I want to make another theorem, another statement. It's called node theorem. So this tells you, this is example 2.2 and 2.3 in Griffiths. So the statement is, so the bound state of nth solution, nth eigenmode, nth eigen solution will have n minus 1 nodes. Okay. Now this node theorem is a very powerful theorem that will allow you to solve many, again sketch many solutions without actually solving it. And you can see the manifestation of this in this problem, that the first one doesn't have any node. Okay. Node means crossing the zero. So first one doesn't have any node. It never crosses the zero except at the boundaries. Second one has one node, because n minus 1 node, right? Third one has 2 nodes. So similarly, if I ask you to solve n equal to 10 solution, you know how it is going to be. It must be 0 here, and it must cross these 9 times. So you can solve like some approximate solution, right? So this is the way to do it. Now this statement is true for any potential that goes to infinity as x goes to infinity. Okay? Which means this potential of course does that, but it is also true for any bounding potential. Which means, let's say I give you a potential like this. Let's say I give you a potential like this, harmonic oscillator. Did any of you study harmonic oscillator in previous sem? Yes. Oh, so you know already. So you know the solution is like this. Right? Yes. But one more thing will happen here. Since this is not going to infinity, like particle in a box, this is still finite, right? So this will leak a little bit here. This will leak a little bit. This is not zero. Right? So you can sketch the solutions of this problem. Similarly, you can do any such potential. Let's say a triangular, a mod x potential. Okay, or a potential of this form, or any arbitrary potential. So you know the solution must be of this form by node theorem. Okay, so it's a very powerful theorem, and that's where I'll stop. And the next class I will elaborate on this statement, that why it should be bounded at lower side, and a little more on node theorem. And then we'll move on to the solution of the rigorous solution of harmonic oscillator problem. Okay. So think about what we learned today. You may not find it exactly the way I told you in a textbook, maybe scattered away in a way, but think about it and try to internalize how to think of a solution of a problem without actually fully solving it. Okay. Yeah, you can stop recording. Yes.